So, imagine waking up one morning, grabbing your coffee, and stepping outside, only to find that the ground where your street used to be is just gone. Not cracked, not slightly damaged, but swallowed up entirely by a massive, gaping void. That's exactly what happened last night in Green Hollow, a town that, until now, had never made the news for anything. But when the earth suddenly collapses with no warning, people start paying attention. Nobody saw it happen. No cameras caught the moment. 1 minute, Oak Ridge Avenue was just another quiet street, and the next, a hole had opened up so deep you couldn't even see the bottom. The first people to notice were the early risers, the ones taking their dogs out for a walk or heading to work before sunrise. Imagine stepping outside and seeing flashing emergency lights reflecting off jagged rock and broken asphalt, people standing around in their robes and slippers, just staring in disbelief. Because this wasn't just a pothole or a minor collapse, it was something else entirely. Authorities rushed to the scene, but nobody had any answers. Was it a sewer line failure? No, the pipes were intact. Maybe an old mining tunnel gave way? Except, there were no recorded mines in this area. And then there was the size of it. Sinkholes aren't unheard of, sure, but this one wasn't normal. It was wide enough to swallow half the street, and from the looks of it, it had no solid bottom, just darkness. As the sun rose higher, geologists and engineers showed up, setting up equipment, taking measurements. Their faces were serious, concerned. And when you see the experts looking worried, that's when you know it's bad. People started throwing out theories. Some said it had to be an underground river, slowly eroding the rock beneath for years, until the surface finally gave way. Others thought it was connected to the recent construction projects nearby. Maybe heavy vibrations had weakened the foundation of the town itself. But then, a third group emerged. The ones who weren't just looking at the hole, but at the sky, at their phones, at the news. Because in the past few months, weird things had been happening all over. Sudden shifts in the ground, unexplained tremors, bizarre reports from other parts of the world. And now, in the middle of Green Hollow, a hole had appeared out of nowhere, with no explanation. The first thing geologists had to consider was whether underground water erosion had been at play, a process so slow and gradual that it often goes unnoticed for years, sometimes even centuries. The idea was straightforward. Over time, groundwater, often slightly acidic, could carve away at the layers of limestone and sediment beneath the town, forming hidden cavities that eventually collapsed under their own weight. It was a known phenomenon, a textbook explanation for many sinkholes around the world. But something about this case didn't fit. Typically, when underground water erosion creates a sinkhole, there are warning signs. Roads begin to crack, buildings shift slightly, trees lean at odd angles. Residents might notice that their doors and windows don't close properly anymore, or that their basements are suddenly damp when they never were before. The process is slow, giving people time to recognize that something isn't right. But here, there had been nothing. No reports of shifting land, no record of any depressions forming in the area. Green Hollow had been stable, its land seemingly secure, until, overnight, it wasn't. That was the first red flag. If water erosion had been the culprit, why had the collapse happened so suddenly? Some scientists suggested that perhaps the erosion had been happening for decades, undetected, and that the collapse had simply been the inevitable breaking point. But when they began analyzing soil samples from around the sinkhole, they found something unexpected. In a typical erosion-related collapse, the sediment layers directly above the cavity tend to be loose and crumbling, showing a pattern of gradual weakening. Instead, the samples from Green Hollow indicated something far stranger. The sediment directly above the hole was compact and undisturbed, as if it had remained solid until the very last moment. It was almost as if, rather than slowly eroding away, the land had been held in place by some unseen force, until it wasn't. This led to another question. If underground water erosion had been responsible, where had the water gone? If an underground river or aquifer had been carving away the rock for years, there should have been visible evidence, some kind of underground reservoir, traces of water seeping into the sinkhole itself. But when geologists lowered cameras and measuring equipment into the darkness, they found nothing. No standing water. No streams running along the exposed rock walls. The ground had simply vanished. That alone was puzzling, but the mystery only deepened when they ran sonar scans of the area. Normally, when a sinkhole opens up, geologists can map out its shape beneath the surface, tracing where the underground cavity had formed. But in this case, the scans didn't detect a simple hollow space. They detected nothing. An empty void stretching deeper than their equipment could measure, with no clear bottom. That was unusual. Most sinkholes, even large ones, have a defined shape. They're caused by predictable geological processes that leave behind traces of their formation. But here, the readings were erratic, almost as if the sinkhole didn't have a floor. The deeper they scanned, the more the signals seemed to scatter, making it impossible to determine just how far down it went. At this point, the scientific team was divided. Some still believed underground water erosion had played a role. Perhaps a previously unknown waterway had existed beneath Green Hollow, carving away the earth before mysteriously drying up. Others, however, began to suspect that something else had happened, something far less conventional. If water hadn't directly caused the collapse, then what had? Had there been a sudden shift in underground pressure? Could there have been a hidden fault line beneath the town, one that had remained undetected for decades? Or had something triggered the collapse from below, something powerful enough to hollow out a massive cavity beneath the earth, all without anyone realizing it? And the biggest question of all, was this sinkhole an isolated event? Or was it just the beginning? The deeper scientists dug, both literally and figuratively, the more questions they uncovered. If water erosion wasn't entirely to blame, then what had allowed such a massive cavity to exist undetected beneath Green Hollow? What force had carved out that void? And more disturbingly, why had it remained structurally intact for so long, only to collapse in an instant? The theories kept coming, each one more unsettling than the last. Some geologists considered the possibility of an underground gas pocket, an accumulation of methane, or another gas that had formed deep within the earth over thousands, or even millions, of years. It was a known phenomenon, though typically associated with oil-rich regions where organic material had broken down over time. When enough pressure built up, such pockets could sometimes cause land to shift, or even explode outward in violent bursts. But there were problems with this theory too. First, there was no history of oil drilling or natural gas extraction in the region. Typically, when underground gas accumulates, signs appear on the surface long before any major event takes place. Small fissures in the ground, odd-smelling emissions, or even cases of flammable gases seeping up through soil and igniting. None of those things had ever been reported in Green Hollow. The land had seemed completely stable. If a gas pocket had been trapped beneath the town, it had done an extraordinary job of remaining undetectable. Then there was the collapse itself. If a gas explosion or rapid release had been responsible, the sinkholes should have been violent. Soil and rock should have been forcefully ejected from the ground. Instead, it was as if the earth had simply given way, crumbling downward in perfect silence. No explosion, no debris field, no outward force, just a quiet and sudden vanishing act. That wasn't how gas blowouts behaved. Yet, when scientists analyzed their samples near the sinkhole, they did detect something strange: elevated levels of certain gases, including hydrogen sulfide, a compound often found in volcanic areas or in places where deep geological activity is taking place. That raised even more questions. Green Hollow wasn't anywhere near an active fault line, nor was it close to any known volcanic systems. The nearest geothermal activity was hundreds of miles away. So where had the gases come from? Some researchers began to wonder whether something deep underground had shifted, something that had disturbed ancient pockets of trapped gas, forcing them toward the surface. But if that were the case, it meant the land beneath Green Hollow wasn't as stable as it appeared. Could the sinkhole be a sign of something much bigger, a warning of deeper geological changes happening far beneath the town? To test that theory, geophysicists set up seismometers around the area, hoping to detect any further activity. If there had been tremors or unusual shifts in the Earth's crust, they would show up in the data. The results, however, were baffling. There had been no significant seismic activity in the area, not in the days, weeks, or even months leading up to the collapse. The ground hadn't shaken. The Earth hadn't warned anyone. That was what disturbed experts the most. Typically, before a major geological event, there are warning signs, minor tremors, subtle shifts in the land, even odd animal behavior in some cases. But Green Hollow had received no such warning. The sinkhole had appeared without prelude, without so much as a whisper of instability. And then came another revelation, one that made the whole situation even stranger. As drone teams continued surveying the hole, mapping its depth and shape, they noticed something odd about the exposed rock layers within the sinkhole walls. In a typical collapse, you'd expect to see distinct layers of sediment, different types of soil and rock stacked upon one another, a clear record of how the land had formed over thousands of years. But here, the layers weren't right. Some were twisted, almost warped, while others seemed completely out of place, as if they had been rearranged by some force long before the sinkhole ever formed. That led to an even more unsettling question: had something else, something long buried, been responsible for weakening the land? Whatever had happened beneath Green Hollow, it wasn't just a simple case of erosion. It was something far more complex, something that had been waiting, hidden below the surface, until the moment was right to reveal itself. As scientists pushed further into their investigation, they began to realize that the layers of twisted and displaced sediment within the sinkhole might be more than just a geological oddity. Something had disturbed the land long before Green Hollow even existed, something powerful enough to shift entire rock formations, warping them in ways that defied easy explanation. The problem was that there was no historical record of major geological activity in the region. Green Hollow wasn't built on an ancient fault line, nor had it been the site of past earthquakes, volcanic eruptions, or dramatic land shifts. On paper, the ground should have been stable. And yet, the evidence suggested otherwise. Had the land been disturbed long ago by an event so rare, so unusual, that it had left no modern trace? That possibility led experts to consider something even more unsettling. Was the sinkhole the result of an ancient subterranean collapse, one that had been building up for centuries or even millennia? If so, it would mean that something below had once given way, leaving behind an enormous underground chamber, a hollow space that had been resting just beneath Green Hollow for untold ages, waiting for the perfect moment to cave in. But what could have caused such a vast void to exist in the first place? One theory pointed toward underground water systems. While Green Hollow had no known caves or extensive underground rivers, that didn't mean they had never existed. Water, over long periods, is a masterful architect of destruction, carving out vast caverns beneath the surface before slowly drying up or rerouting elsewhere. If an ancient river had once flowed beneath the town, it could have left behind a system of empty chambers, their ceilings growing ever thinner with time, until one day, they could no longer support the weight above them. This idea made sense in many ways. In other parts of the world, massive sinkholes had formed due to underground water erosion, often in areas rich in limestone or other easily dissolvable rock types. These karst formations could remain hidden for thousands of years before finally collapsing under the weight of modern construction, human activity, or even minor natural shifts. But there was a problem with this explanation. Green Hollow wasn't known for having the type of rock formations that typically led to karst sinkholes. Its bedrock was supposed to be solid, dense, stable, and not the kind to be quietly eaten away by underground water flows. If water erosion was responsible, then scientists had severely underestimated just how much the landscape had changed beneath their feet. And then, there was the size. Most sinkholes caused by water erosion had predictable limits, typically forming in places where underground rivers or caves had once existed. But Green Hollow's sinkhole was unusually large, far wider and deeper than what would normally be expected. If this was caused by water, then it had to have been an extraordinarily vast and long-lasting process, one that had taken thousands upon thousands of years to create such an enormous void. Geologists sent exploratory drilling teams into the area, hoping to find traces of the long-lost water system that might explain the collapse. If they could uncover ancient deposits of mineral-rich sediment, it could prove that a river or underground lake had once been present. But when the samples came back, they raised more questions than answers. The sediment layers contained something unusual, traces of organic material that shouldn't have been there, at least not at the depths where they were found. Some of the material resembled decayed plant matter, but not the kind that would be expected in an underground collapse. Instead, it appeared to be remnants of vegetation that had once existed on the surface but had somehow ended up buried far below, compressed and preserved in a way that suggested something had violently displaced it long ago. This discovery sent scientists scrambling for answers. If the land had once been reshaped by some event powerful enough to bury entire layers of plant life beneath Green Hollow, what could have caused it? Could it have been a landslide? An ancient flood? Or was it something else, something even more difficult to explain? At this point, theories began to diverge. Some experts stuck with the idea of underground water erosion, insisting that a massive, hidden cave system had once existed beneath the town. Others started to suspect that something far more sudden and catastrophic had taken place deep in the past, an event that had rearranged the landscape in ways that no one had ever realized. As the investigation into the origins of the sinkhole deepened, another hypothesis began to gain traction: the possibility of tectonic activity far beneath Green Hollow. While the region was not located near any known major fault lines, this did not rule out smaller, hidden tectonic shifts. Geologists proposed that a minor fault, previously undetected by conventional methods, might have been the source of the sinkhole's formation. Unlike large fault lines that could cause earthquakes or visible surface shifts, a small, dormant fault might have remained hidden for centuries, only to shift dramatically under certain conditions. This idea was compelling. For one thing, the Earth's tectonic plates are constantly shifting, and while major earthquakes tend to capture all the attention, smaller, more localized shifts could cause immense disruptions without warning. If a previously dormant fault had experienced movement, perhaps due to the slow accumulation of pressure from nearby plate movements, this could easily cause the ground above it to buckle or collapse. The fact that the sinkhole was so large and so sudden seemed to fit this theory. It suggested that the stress beneath the surface had reached a tipping point, leading to an unexpected release of pressure. But this theory had its own set of complications. To begin with, small, localized faults typically don't lead to such massive land shifts. The land above such faults tends to exhibit only subtle signs of change, small cracks in the earth or shifts in the soil. Yet, Green Hollow's sinkhole was enormous, seemingly appearing out of nowhere overnight. The idea that a subtle tectonic shift could cause such an extreme event was difficult to reconcile. Still, there were instances in other parts of the world where localized fault activity had created sinkholes, though these examples were incredibly rare and often chalked up to freak occurrences. To further complicate the theory, the region around Green Hollow showed no signs of past tectonic disturbances. Unlike areas located near the edge of tectonic plates, where seismic activity is a regular feature, Green Hollow had always been considered relatively stable. No major earthquakes had been recorded in the area for hundreds of years, leading some experts to question whether tectonic activity could truly be the cause of such a large-scale collapse. If tectonic shifts were responsible, it would mean that something had triggered this hidden fault to suddenly move after being dormant for so long, something that had been overlooked in previous geological surveys. Despite the uncertainties, this theory gained some traction when seismic readings from the area started to reveal unusual low-frequency vibrations deep below the surface. These readings were faint but consistent, indicating that there was some form of movement occurring in the Earth's crust far beneath Green Hollow. While these signals were not strong enough to cause immediate concern, they were enough to suggest that the ground beneath the sinkhole might be far more active than anyone had previously realized. As the seismic data was analyzed, scientists began to draw parallels with other recent sinkhole events in regions that were not traditionally known for tectonic activity. One notable example was the catastrophic sinkhole that opened in the small town of Guatemala City in 2010. That sinkhole, which swallowed an entire intersection, had been caused by the collapse of an underground cavity following a period of unusual seismic activity. Could something similar have occurred in Green Hollow? The possibility seemed increasingly likely, but there was still no clear evidence to confirm it. Another troubling aspect of the sinkhole's formation was the lack of surface warning signs. In many cases, sinkholes begin as small depressions or cracks in the ground that gradually expand as the earth shifts below. But Green Hollow's sinkhole appeared without warning, seemingly catching everyone off guard. This made the idea of a tectonic cause even more perplexing. If a fault had caused the collapse, why was there no observable movement in the months or years leading up to the event? Why had the surface remained stable, giving no indication of the catastrophe brewing beneath? To answer these questions, geophysicists began to look at the rate at which the tectonic plates themselves were moving. Earth's plates, despite being constantly in motion, shift at incredibly slow rates, typically a few centimeters per year. Yet, in some cases, these movements could trigger a slow buildup of pressure in previously stable regions, until that pressure was finally released in the form of an unexpected event. The issue was that this type of tectonic movement often takes thousands, or even millions of years to produce a noticeable effect. For a sinkhole to open suddenly, there had to be a unique set of conditions that allowed it to happen in such a rapid and dramatic manner. This raised another theory. Could there have been an interaction between tectonic pressure and another natural force? Perhaps a combination of factors: minor fault movement, extreme weather events, and even human interference, had all worked together to trigger the collapse. This kind of multi-layered event was certainly possible, but it would require a deep and nuanced understanding of how these forces could combine to create such a disaster. The complexities of such an event were not lost on the experts, and they continued to study the area for any subtle changes that might indicate other contributing factors. As more data was gathered, another possibility emerged, one that took into account not just the movement of the Earth, but the larger environmental context. The possibility that the region had been destabilized by extreme weather or climate-related events began to gain more attention. While Green Hollow had been relatively quiet in terms of tectonic activity, it had not been free from weather events. The region had recently experienced a series of unusually heavy rains, as well as shifts in local atmospheric pressure. Could these environmental changes have contributed to the sudden collapse of the land? Extreme weather patterns had been known to affect the stability of the Earth in unexpected ways. In some cases, heavy rainfall can saturate the ground, weakening it and making it more susceptible to sudden shifts. In other cases, rapid temperature fluctuations can cause the ground to expand and contract, leading to stress on underground formations. Could the unusual weather conditions in the weeks before the sinkhole's appearance have been the catalyst for this event? This was another avenue of investigation that could help explain the sudden and seemingly inexplicable nature of the collapse. Yet, as with every theory, questions remained. Would these environmental conditions alone have been enough to cause such a massive sinkhole? Could the Earth have been primed for collapse in ways that no one had anticipated? The deeper the experts dug into these possibilities, the more complex the situation became. What was certain, however, was that Green Hollow's sinkhole wasn't an isolated incident. Something was shifting beneath the surface, and whatever that force was, it had left behind an unmistakable warning. As the investigation continued, a surprising twist emerged from the study of the area's geology. Experts began to speculate that the sinkhole's origin might not be solely the result of tectonic activity, environmental factors, or even the weather. Instead, there was growing consideration of a phenomenon known as karst topography, which involves the dissolution of soluble rocks like limestone, dolomite, or gypsum. These types of rocks are particularly susceptible to erosion caused by natural forces like water, acid rain, and even organic acids produced by plant and animal matter. Over time, this process can create vast underground networks of caves, tunnels, and voids, some of which can collapse with little warning. Karst topography was already known to be a significant cause of sinkholes in regions across the globe. In fact, many of the world's most famous sinkholes, like the ones found in Florida, China, and Mexico, have been linked to karst processes. In these regions, the constant interaction between water and soluble rocks causes underground cavities to expand until they become so large and unstable that the land above them collapses entirely. What was intriguing about Green Hollow was that, despite its lack of history in karst formation, it was situated in an area where the geological conditions seemed conducive to such a phenomenon. Geologists quickly realized that the region surrounding Green Hollow contained layers of limestone deep beneath the surface. This raised the possibility that, over thousands of years, water had been slowly seeping through cracks in the rock, eroding it from the inside. While this process was typically slow and unobtrusive, it had the potential to build up enough pressure and instability to cause a sudden collapse, especially if there had been a significant influx of rainwater or a surge in groundwater levels. This influx could easily accelerate the dissolution of the limestone, destabilizing the ground above it. Interestingly, the geological surveys of Green Hollow had never identified any significant signs of karst development. The land above had appeared solid and stable, offering no indication of the expansive underground tunnels that might have been forming over the centuries. This posed the question: had these underground cavities been forming so slowly that no one had noticed them? Or was there a more recent event, perhaps a sudden change in the groundwater flow, that had triggered the collapse of the surface? The presence of caves and tunnels beneath the Earth's surface posed a major risk, as any disturbance could cause catastrophic shifts. What many didn't realize was that sinkholes caused by karst processes could be unpredictable. Even though water erosion might seem like a gradual process, the instability that built up over time could lead to rapid and dramatic land shifts. A cave that had been forming for hundreds of years might suddenly collapse within a matter of days, or even hours, once it had reached a critical point. One theory that began to gain traction involved an unusual change in the local hydrology. Recent months had seen increased rainfall, and it was hypothesized that this excess water had permeated deeper into the ground, triggering an increase in the dissolution process. The local groundwater had risen to levels that might have exposed previously hidden weaknesses in the limestone layers, hastening the collapse of the land above. This theory had a certain elegance, as it accounted for both the sudden appearance of the sinkhole and the absence of visible warning signs. However, this new theory also prompted a series of questions that were difficult to answer. If karst processes were the main cause of the sinkhole, why had the region remained so stable for so long? After all, sinkholes caused by karst topography were not uncommon in areas where the underlying rock was primarily limestone, yet they tended to occur slowly over time, often resulting in smaller depressions before the larger collapse. The suddenness of the Green Hollow sinkhole was still puzzling. It suggested that something else might have contributed to the collapse, something that accelerated the process. As the scientific community delved deeper into this possibility, another, more speculative idea began to emerge. What if the sinkhole was somehow connected to larger shifts occurring deep beneath the Earth's crust? Could it be that the subterranean pressure from tectonic activity had created a chain reaction, one that not only affected the surface directly but also disrupted the underground karst systems, causing them to collapse more rapidly? Though this was an untested hypothesis, it added a new layer of complexity to the situation. The interplay between tectonic forces and karst processes had never been fully understood, and the possibility of these forces combining to create a massive sinkhole was an exciting and dangerous prospect. To add to the mystery, some researchers began to look into the human influence on the land in Green Hollow. Were there activities such as mining, construction, or even agricultural practices that might have inadvertently triggered the collapse? In many cases, human actions had been shown to exacerbate natural geological processes. The mining of limestone, for example, had caused significant destabilization in certain regions, and even the clearing of large swathes of land for agriculture could have caused subtle shifts in the land's structure. Could the locals have unknowingly created the perfect conditions for the sinkhole? Experts were quick to investigate this line of thought, but so far, they found little to suggest any direct human activity had contributed to the collapse. No mining had taken place in the immediate vicinity of Green Hollow, and there were no large-scale construction projects that would have disturbed the geological balance of the region. Still, the possibility that human activity played a part, even in a minor way, remained a tantalizing question, one that required further research. As the investigation into Green Hollow's sinkhole continued to unfold, it became increasingly clear that the true cause of the collapse might not be fully understood for some time. Theories continued to multiply, each one offering its own explanation but also raising new questions. Was the sinkhole the result of a slow and steady geological process, like karst erosion, or had it been triggered by some external event, such as tectonic shifts or extreme weather patterns? Or was it a combination of these factors, interacting in ways that had never before been seen? As the investigation into the sinkhole's origin progressed, an unexpected twist emerged when a team of researchers proposed the possibility of a vibrational trigger that could have caused the collapse. The theory suggested that the sinkhole might not have formed from traditional geological processes, but rather due to a sudden, intense vibration traveling through the Earth's crust. While this concept may sound outlandish at first, it was rooted in scientific principles that had been observed in other geological events. Vibrations in the ground, whether caused by a distant earthquake, a series of explosions, or even something as simple as heavy machinery operating nearby, could potentially disrupt subterranean layers in ways that lead to a sudden collapse. To understand this theory, one had to first grasp the power of seismic waves. Seismic waves are the energy waves that travel through the Earth, often caused by the shifting of tectonic plates. These waves can travel vast distances, but in many cases, they're too faint to cause any noticeable effects at the surface. However, in specific circumstances, when these waves strike a particularly weak point in the Earth's crust, the results can be catastrophic. A tremor might be enough to destabilize underground caverns, causing them to collapse, sometimes in an instant. But what would cause such a tremor near Green Hollow? Surprisingly, researchers found that, though the area had not experienced any earthquakes or volcanic activity in recent memory, there had been a marked increase in seismic activity in nearby regions. The neighboring mountain range had seen a surge in small, barely detectable tremors, and some of these seismic events might have been strong enough to travel through the ground and influence the geological structure of Green Hollow. It was as though the vibrations from distant tectonic movements had slowly accumulated and, over time, reached a critical threshold. Once that threshold was breached, the already fragile ground of Green Hollow simply couldn't hold up. What made this theory particularly intriguing was the idea that the local geology might have been uniquely vulnerable to these kinds of vibrations. For example, the presence of certain types of soil and rock formations could have amplified the seismic waves, causing them to have a more pronounced effect than they would have in other areas. The local limestone, when combined with clay-rich soils, might have acted as a perfect conduit for the vibrations, funneling the energy deep into the earth where it caused an unexpected collapse. In this way, the sinkhole might not have been the result of gradual erosion or surface weathering, but a sudden shockwave, a vibrational pulse that hit at just the right moment to trigger the collapse of the ground above. But this theory also led to a series of questions that would require further investigation. How could a vibration, which was so subtle and so distant, manage to destabilize such a large section of land? How could Green Hollow, an area that had long appeared stable, suddenly become susceptible to these vibrational forces? The answers remained unclear, but the implications of this theory were far-reaching. It meant that sinkholes could potentially form in areas far removed from any direct tectonic activity, and that even the faintest of seismic disturbances could set off a chain reaction of events. As the debate continued, some researchers began to draw parallels between this event and other sinkholes that had occurred in regions far from major fault lines. In many of these cases, small seismic events, such as localized mining explosions, the use of heavy machinery, or even the vibration from traffic, had been linked to the sudden formation of sinkholes. This suggested that vibrations might play a much larger role in the formation of sinkholes than previously realized. If this was true, it could change the way geologists thought about sinkhole risks, particularly in urban areas where human activity regularly sends seismic waves through the ground. Furthermore, there was the possibility that human-made vibrations had played a more direct role in Green Hollow's collapse. Mining activity had been occurring a few miles away, and while the operations were relatively small-scale, the constant use of large machinery might have been sending vibrations through the ground, slowly weakening the area. Though these vibrations might have seemed insignificant on their own, when combined with the natural seismic activity from distant earthquakes, they could have compounded the effects, resulting in the catastrophic collapse. This raised new questions about the unintended consequences of industrial activity and how the vibrations caused by human progress could have unforeseen, far-reaching impacts on the natural world. Another intriguing angle involved the idea of underground water movement, particularly in relation to vibrations. Researchers began to hypothesize that water seeping into subterranean voids, combined with the shockwaves from distant seismic activity, might have contributed to the collapse. Water in underground caverns is known to be a powerful force, eroding rock and destabilizing soil over time. If the vibrations caused the water to move suddenly, it might have exerted enough force to destabilize the already weakened structure of Green Hollow. This added a new dimension to the theory of vibrations, suggesting that it wasn't just the seismic waves themselves that were responsible for the collapse, but the interaction between these waves and the water trapped deep underground. As more data was gathered, the concept of vibrational triggering became a central theory in the search for the sinkhole's cause. The idea that subtle, seemingly insignificant tremors could have such a profound impact on the Earth's surface was both captivating and unsettling. It suggested that the Earth was far more sensitive to small changes than scientists had once believed, and that the forces at work beneath our feet were more interconnected than anyone had ever imagined. The theories surrounding Green Hollow's sinkholes seemed to be growing ever more complex, weaving together elements of geology, human influence, and the unpredictable nature of seismic activity. With each new discovery, it became more and more clear that the sinkhole was not simply a freak occurrence, but part of a much larger pattern of interconnected events that had yet to be fully understood. Each layer of research uncovered new details that only served to deepen the mystery of what had caused the collapse. But what was most striking was that, despite all the scientific expertise brought to bear on the problem, the full truth remained just beyond reach. The investigation continued to evolve as researchers began to consider an even more mysterious factor: the role of underground gas emissions. While the idea might initially seem out of place, the more scientists delved into the sinkhole's peculiarities, the more they realized that gases trapped beneath the Earth's surface could have played a significant part in destabilizing the ground. These gases, often formed by decaying organic matter, can accumulate in large pockets deep beneath the surface, exerting pressure on surrounding rock formations. Over time, the pressure from these gases can weaken the structural integrity of the rock above them, eventually causing the ground to give way. In many cases, gas pockets are harmless, remaining inert for long periods. However, when these pockets are disturbed, whether by natural seismic activity or human intervention, there is the potential for catastrophic collapse. The gases, primarily methane or carbon dioxide, may act like a slow-release trigger. In areas where the Earth's crust is already fragile or porous, the release of gas can create a domino effect, causing the surrounding soil and rock to lose their cohesion and fall inward. Researchers were particularly intrigued by the possibility that, in the case of Green Hollow, some unseen underground event, perhaps a shift in the local water table or the buildup of excess pressure from below, had disturbed such a gas pocket, leading to the massive sinkhole. Interestingly, the sinkhole's rapid formation seemed to suggest that something more than just geological instability was at play. A significant factor in this theory was the rate at which the sinkhole appeared. Unlike many sinkholes, which take weeks, months, or even years to develop, Green Hollows appeared almost overnight. This sudden collapse seemed to align more closely with the idea of a pressurized pocket of gas being released suddenly, like the top of a shaken soda can, spilling out when the cap was removed. The trapped gases, once freed from their underground confinement, would have triggered a sudden and violent collapse of the surface, resulting in the enormous hole that was now the focus of so much attention. One specific question that kept arising was why this particular location seemed to be a hotspot for such activity. Why did Green Hollow experience a sudden sinkhole while nearby regions remained unaffected? The theory that underground gas pockets were responsible offered a potential answer. The area surrounding Green Hollow had a history of deep soil and rock formations, which could have allowed for the slow accumulation of gases over centuries. What made this region particularly vulnerable was the presence of natural fractures in the Earth's crust. These fractures could have acted as conduits, allowing the gas pockets to form and expand in an unstable environment. In the right conditions, the release of gas through these fractures could cause the land above to sink rapidly and without warning. The involvement of gas emissions opened a host of additional questions. For one, could the increasing activity in nearby industries be contributing to these subterranean gas pockets? Mining operations, oil drilling, and even fracking, all of which involved the use of machinery to penetrate deep into the Earth's surface, might be inadvertently disturbing the fragile balance of gases trapped beneath the ground. While these operations were often tightly regulated, the sheer scale of some of these projects, combined with the complexity of geological systems, might have been enough to destabilize previously untouched layers of rock. This line of inquiry raised concerns not only about the specific incident at Green Hollow, but about the long-term impact of human intervention on the Earth's underground systems. Moreover, the question of monitoring and predicting sinkholes due to gas emissions became a critical concern. Unlike earthquakes or volcanic eruptions, which leave clear warning signs through seismic activity or shifts in magma movement, gas buildup beneath the surface is incredibly difficult to track. Traditional geological monitoring methods often focus on more visible or tangible signs of instability, such as changes in the landscape, seismic vibrations, or shifts in groundwater levels. But gas pockets, particularly those located deep below the surface, are largely invisible to current monitoring techniques. Without a more advanced system to detect these unseen pressures, scientists feared that sinkholes caused by gas emissions might remain unpredictable, potentially leading to more incidents like Green Hollow. As the conversation about gas emissions and their role in sinkhole formation continued, some experts began to point to a growing body of research that suggested global warming could be influencing the buildup of underground gases. In recent decades, the Earth's changing climate had caused fluctuations in temperature and pressure at various levels of the Earth's crust. These fluctuations could, in theory, affect the natural processes that trap gases underground, either speeding up or slowing down their release. Warmer temperatures could also alter the chemistry of the soil and rock, potentially causing certain compounds to become more volatile or reactive. This added another layer of complexity to the mystery surrounding Green Hollow's sinkhole, suggesting that environmental shifts, beyond just local events, might have a role in the destabilization of the ground. One of the most peculiar aspects of sinkholes like the one in Green Hollow is the speed at which they appear. Unlike traditional sinkholes that develop over long periods, some sinkholes seem to form almost overnight, as if the Earth was simply waiting for a single disturbance to trigger a collapse. Scientists have long speculated that certain geological conditions can cause the surface to suddenly give way, but one theory that continues to emerge from ongoing research is the concept of what is known as the ticking clock effect. This theory suggests that, while the process leading to a sinkhole might take years or even centuries to unfold, it could remain dormant until a particular event triggers it. This event might not necessarily be a massive seismic shift or a dramatic weather change, but rather a subtle disturbance, a small tremor or a series of unusually heavy rainfall, enough to set off the final collapse. Essentially, the Earth may already be in a precarious state, with the sinkhole just waiting for the right conditions to expose its hidden dangers. The ticking clock theory is difficult to prove because it requires understanding the precise balance of pressures and conditions below the surface, but it offers a compelling explanation for why certain sinkholes appear without warning. In Green Hollow, some scientists have wondered if a series of microseismic events, which would otherwise be undetectable by most sensors, could have acted as a trigger. These microseisms, often imperceptible to humans, might be the result of small shifts deep beneath the surface. While too small to feel or even measure in real time, over time, they could accumulate and cause enough instability to start a chain reaction. The pressure from these subtle movements, combined with an already vulnerable underground structure, could create just enough stress for the Earth's surface to give way, leading to the massive sinkhole that formed overnight. This theory presents the idea that the ground beneath us is constantly in flux, but it's only when those fluctuations cross a certain threshold that the surface crumbles. Another compelling angle to consider is the potential involvement of underground water systems in this process. It's well known that the erosion of subterranean rock formations caused by water is one of the primary factors behind sinkholes. However, in some cases, the role of water may be more complex than previously thought. Recent research has suggested that underground rivers or aquifers, which are often invisible to us, can change course or become overloaded in ways that are difficult to predict. These shifts might occur so gradually that they aren't noticeable at the surface, but over time, the buildup of pressure could reach a breaking point. In the case of Green Hollow, experts hypothesize that a hidden aquifer beneath the area may have been the key to the sinkhole's sudden appearance. If the groundwater levels had shifted due to prolonged rainfall or changes in nearby water extraction activities, the flow beneath the earth could have altered the pressure dynamics in the region. As the water eroded the bedrock over time, it may have created voids, hidden spaces beneath the surface that were invisible to those above ground. These voids, though small, could have become unstable, leading to a collapse that was both sudden and massive. The mystery of why this particular sinkhole formed when it did may then be linked to the unnoticed shifts in underground water channels. In such cases, there's also the possibility that human activity, such as the over-extraction of groundwater or the construction of tunnels and roads, could exacerbate the natural erosion of these underground rivers. The development of new infrastructure in areas with fragile geology could create a scenario where the human touch, even if unintended, accelerates the process of sinkhole formation. In regions like Green Hollow, where construction has steadily increased over the years, experts believe that the complex relationship between natural water flow and human interference may have been a critical factor in setting the stage for disaster. Furthermore, the combination of natural forces and human activity could have led to a situation where the sinkhole's formation was not an isolated incident but part of a larger pattern of ground instability in the region. Environmental surveys from the past decade revealed an uptick in sinkhole occurrences in areas near significant human development projects. These included large-scale construction sites, mining activities, and agricultural expansion, all of which can alter the local environment in unpredictable ways. The more researchers explored the connection between these human activities and natural events, the more they began to consider the possibility that the occurrence of sinkholes like Green Hollow might not be entirely random. But even as all these theories began to take shape, another important factor started to emerge from discussions within the scientific community: the potential impact of geothermal activity beneath the surface. While this may seem unrelated to sinkholes at first glance, there's growing evidence that volcanic activity, specifically geothermal pressure, could play a significant role in destabilizing certain regions. When magma chambers beneath the Earth's crust build up too much pressure, they can cause local ground shifts that weaken surface rock layers. Over time, these geological stresses can lead to cracks and fractures in the Earth's surface, some of which may grow large enough to create sinkholes. While there's no immediate evidence of active volcanic activity in Green Hollow, the possibility that geothermal pressures were at work beneath the surface is an intriguing one. In areas where geothermal systems are present, even slight changes in pressure can lead to noticeable shifts in the ground above. Scientists have even suggested that a minor geothermal event could create a ripple effect, spreading far from the actual source of pressure and causing a sinkhole to form at a seemingly unrelated location. This theory introduces the idea that what we perceive as random geological events might actually be connected to larger, more complex systems of pressure deep within the Earth. While it may be difficult to pinpoint geothermal activity in a specific location, it's a theory worth considering when examining sudden and mysterious sinkhole formations. As we continue to explore the depths of this geological mystery, it becomes increasingly evident that a singular explanation for the Green Hollow sinkhole may never fully satisfy the complexities of the event. One of the more fascinating avenues of investigation is the idea that the Earth's crust itself may be far more dynamic than traditionally believed. Geophysicists are increasingly pointing to the idea of crustal flexure, the way that the Earth's surface can bend and flex in response to forces acting beneath it, as a key factor in sinkhole formation. Crustal flexure occurs when pressure builds up beneath the surface, causing the Earth's outer shell to shift slightly. Over time, this subtle shifting can create cracks and weaknesses in the surface layers, which can eventually lead to a collapse. What makes this theory so intriguing is that it doesn't require any major seismic event to trigger the collapse. Instead, it suggests that even small, gradual forces, like changes in the weight distribution of the Earth's mantle or shifts in tectonic plates, could cause significant impacts on the surface. When these forces accumulate over time, the Earth's crust could experience localized bending or warping, weakening certain areas until they can no longer support the weight of the surface above them. In some cases, this bending may go unnoticed for years, even centuries, until one small additional trigger, such as heavy rainfall or a minor tremor, causes the final collapse. For the researchers in Green Hollow, this theory began to gain traction as they examined the geology of the region. Through detailed seismic imaging, scientists were able to detect signs of shifting in the Earth's crust far beneath the surface. This shifting, while not enough to cause a full-scale earthquake, might have been just enough to weaken the layers of rock in the region and set the stage for the sinkholes formation. As researchers began to piece together this idea, they realized that such subtle movements might be more common than previously thought, suggesting that sinkholes could be the result of long-term geological processes rather than short, dramatic events. Another potential cause that scientists have explored is the role of ancient geological features that may have been hidden for millennia beneath the surface. One theory proposes that the region surrounding Green Hollow might have once been the site of an ancient underground cavern system, possibly formed by long-extinct rivers or other natural forces. Over time, these underground systems could have collapsed, leaving behind massive voids in the Earth's crust. While these voids may have been stable for eons, they might not have been able to withstand modern disturbances, such as new infrastructure projects, or even the simple weight of an increasing population in the area. When new stresses were placed on the ground above these ancient voids, the collapse could have triggered a sinkhole, forming seemingly out of nowhere. As scientists dug deeper into the region's past, they discovered evidence of ancient cavern systems and eroded cave networks that had long since collapsed. These networks, while no longer active, may have left behind weak points in the ground that became more vulnerable over time, especially with the additional pressure caused by human development. The challenge for researchers now was determining whether these ancient geological features played a role in the formation of the Green Hollow sinkhole. The idea that ancient systems of underground caves or rivers could cause such a dramatic event seemed almost surreal, but as the evidence mounted, it became clear that the Earth's geological history could hold key insights into present-day sinkhole formation. At the same time, the researchers began to focus more intently on the role of permafrost thaw, the phenomenon that occurs when previously frozen ground begins to melt due to rising temperatures. While this process is typically associated with polar regions, there are parts of the world, including areas in Green Hollow, where permafrost has been present for centuries, if not millennia. As temperatures gradually rise, this once frozen ground begins to thaw, causing significant changes in the way that the soil and rock behave. The result is a gradual release of water, which can further erode underground structures, contributing to the weakening of the Earth's surface. In areas where permafrost has begun to thaw, the rate of sinkhole formation has risen sharply. As the ground thaws and releases water, this additional fluid can exacerbate the erosion of the rock below the surface. Over time, these factors can lead to the creation of voids in the Earth's crust, which are unstable and prone to collapse under the right conditions. In Green Hollow, researchers began to wonder whether thawing permafrost, combined with local climate change, could have been the hidden catalyst for the sudden appearance of the sinkhole. While not typically associated with sinkhole formation in warmer climates, this theory was gaining traction as researchers examined the subtle environmental changes that have taken place in the region over the past few decades. The thawing of permafrost, and its potential connection to sinkhole formation highlights a larger issue that is becoming increasingly urgent: the unpredictable nature of climate change. As global temperatures rise, we are witnessing shifts in the Earth's systems that were previously thought to be stable. For instance, the increasing frequency of extreme weather events, floods, droughts, and intense heat waves, has been linked to rapid geological changes in certain regions. As the Earth's climate continues to warm, it's becoming clearer that the land beneath our feet is undergoing its own transformation, one that we may not yet fully understand. The impact of climate change on geological processes is not limited to thawing permafrost or extreme weather events. Even subtle shifts in atmospheric pressure can influence the behavior of underground water systems and mineral deposits. This is something that researchers in Green Hollow began to consider when they observed a sudden increase in sinkhole activity across the region. While no single event could explain the sudden rash of sinkholes, it became clear that the Earth's changing climate could be contributing to an environment that is increasingly prone to these dramatic collapses. In this context, sinkholes like the one in Green Hollow may not be isolated occurrences at all, but part of a broader pattern that reflects the changing dynamics of our planet. The very forces that shape the Earth's surface, tectonic plates, underground water systems, and even atmospheric pressure, are all interconnected. When these forces are disrupted, whether by natural events or human intervention, the consequences can be catastrophic. The Green Hollow sinkhole might just be a glimpse into what could become a more frequent phenomenon as the Earth continues to respond to the pressures of climate change and human influence. This realization prompted researchers to look more closely at the environmental trends surrounding sinkhole formation in recent years. They found that areas that had once been considered stable were now experiencing sudden, unexpected sinkholes, even in places that had never been known for such geological activity. The rise of sinkholes across various parts of the world seemed to be more than just a coincidence. It was a sign that something deeper, something far more profound, was at work beneath the surface. As the investigation into the Green Hollow sinkhole gained momentum, the government found itself under increasing pressure to address the emerging crisis. The public, understandably alarmed by the size and sudden appearance of the sinkhole, began demanding answers. Local communities feared the event could be a sign of something far worse, a disaster waiting to happen. Initially, government officials responded cautiously, releasing only brief statements about the ongoing investigations and assuring the public that they were closely monitoring the situation. However, as the scale of the problem became more apparent, and more sinkholes began to emerge in nearby regions, their stance shifted dramatically. At first, the response seemed more reactive than proactive. Local emergency management teams were mobilized, and resources were allocated to deal with the immediate aftermath of the Green Hollow sinkhole. Emergency evacuations were carried out for those living in the immediate vicinity, and temporary shelters were set up to house displaced families. However, despite these efforts, it became increasingly clear that the government's initial response lacked a long-term plan for addressing the root causes of the sinkhole or preventing future ones. This left the public frustrated, with many questioning whether the government truly understood the magnitude of the threat or if they were simply reacting to a crisis that had already spiraled out of control. As weeks passed and the media continued to focus on the unfolding crisis, the government began to shift its focus. This wasn't just a localized issue anymore, it was a national concern, one that could potentially affect large swaths of the population. In response, they formed a specialized task force made up of experts from various fields: geologists, climatologists, emergency management specialists, and urban planners. Their goal was to assess the broader implications of the sinkhole and its potential for triggering similar events across the country. While this was an important step, it also highlighted how ill-prepared the government had been for a crisis of this magnitude. The formation of the task force seemed almost too little, too late. Public backlash mounted, with critics accusing the government of dragging its feet and not taking the threat seriously enough. Activists, scientists, and even local politicians began calling for more immediate action. The most vocal of these critics argued that the government was too focused on damage control rather than addressing the underlying causes of the sinkhole. They pointed to the increasing number of sinkholes across the country as evidence that the nation's infrastructure and environmental monitoring systems were woefully inadequate. If the government wasn't willing to invest in proactive solutions now, they warned, they would be caught off guard by even more catastrophic events in the future. In an attempt to calm public unrest, government spokespeople began appearing in the media to assure citizens that steps were being taken. They promised that a thorough investigation would take place, with plans to address the issues at the heart of the Green Hollow sinkhole. But their statements seemed to ring hollow to many, especially as new sinkholes continued to appear in other regions. It was becoming increasingly clear that the government's response was more about damage control than genuinely addressing the systemic issues that were driving the phenomenon. Behind closed doors, there were debates at the highest levels of government about how to move forward. Some factions within the government pushed for immediate action to address climate change and its potential role in the sinkhole crisis. Others advocated for a more traditional approach, focusing on improving infrastructure and better monitoring of geological hazards. Meanwhile, a few individuals argued that the Green Hollow sinkhole could be a one-off event, not necessarily a symptom of a larger, more troubling trend. This division within the government further delayed a cohesive and comprehensive response. As the situation in Green Hollow continued to unfold, the government found itself under pressure from both sides. On one hand, there was a growing demand for more funding and resources to deal with the immediate fallout of the sinkhole. On the other, environmentalists, scientists, and concerned citizens were calling for a broader, more sustainable approach, one that would address the root causes of the phenomenon and prevent similar events in the future. The task force, while diligent, could only do so much with the resources and funding allocated to them. They continued to investigate the geological conditions of the region, but without significant support from the government, their efforts were slow and often insufficient. The lack of a clear plan led to a growing sense of distrust among the public. People began to wonder if their government had the necessary expertise or willpower to tackle such an unprecedented crisis. How could they trust officials who seemed caught off guard by the very phenomenon they were supposed to prevent? It wasn't just the sinkholes that were at stake, it was the government's credibility. If they couldn't effectively handle this situation, what other threats were they unprepared for? Amid growing frustration, local leaders began to take matters into their own hands. Many of them had no choice but to rally their communities and take action where the government had failed. In some regions, local authorities began implementing their own safety measures, such as strengthening building codes, improving flood drainage systems, and even offering temporary financial aid to those affected by the sinkholes. These efforts, though well-intentioned, were largely piecemeal, lacking the coordination and resources necessary to fully address the issue. Nonetheless, they served as a stark reminder of how the failure of higher levels of government could lead to a disjointed and inefficient response. Meanwhile, environmental organizations began to gain traction in pushing for more stringent regulations on land use and infrastructure development. Many believed that the government's failure to take climate change seriously, combined with poor urban planning, had contributed to the disaster. Their calls for action grew louder, with increasing numbers of citizens joining the protests and rallies in support of more aggressive environmental policies. The lack of leadership at the national level and the growing demands for accountability led to a reckoning of sorts. Citizens began to question whether their government could ever be trusted to handle the complex issues surrounding environmental degradation, urbanization, and climate change. It wasn't just about the Green Hollow sinkhole anymore. It was about the future of the country, and whether the government could act decisively enough to mitigate the mounting environmental challenges ahead. As the crisis grew, discussions shifted toward finding solutions and preventative measures to tackle the increasingly frequent and severe sinkholes. The government, now under intense pressure, quickly realized that piecemeal responses would no longer suffice. The situation had escalated beyond the realm of simple disaster management. What was needed was a comprehensive, multifaceted approach to address not just the immediate damage, but also the underlying causes, to prevent further disasters in the future. One of the first and most urgent solutions that emerged from the summit was the need for a nationwide geological survey. The sheer scale of the sinkholes had caught many by surprise, and the government now understood that they needed to fully understand the state of the land beneath their feet. This meant conducting detailed investigations into the stability of the Earth's crust, particularly in areas where sinkholes were most common. Leading geologists and environmental scientists argued that without this crucial data, it was impossible to predict where the next sinkhole might appear or how severe it could be. Experts called for new technologies, such as ground-penetrating radar and seismic sensors, to be deployed across the country to create a comprehensive map of potential sinkhole zones. However, conducting a nationwide survey would take time that the government could not afford. So, in the short term, authorities decided to focus on the areas most at risk. Special teams of experts were dispatched to areas that had already experienced sinkholes, as well as to regions that were showing signs of instability. The goal was to assess the ground conditions and identify early warning signs. Scientists suggested that sinkholes could be detected before they formed, using advanced monitoring techniques that track subtle shifts in the Earth's surface. By detecting these shifts early, authorities could issue warnings and evacuate people before disaster struck. Another critical aspect of the solution was reinforcing infrastructure. Many of the areas affected by the sinkholes had seen their roads, bridges, and buildings crumble under the pressure of the collapsing ground. This made it clear that the country's infrastructure was woefully unprepared for such events. The government launched an initiative to retroactively strengthen existing infrastructure in sinkhole-prone areas, using new technologies that could make buildings and roads more resilient to ground movement. One promising approach involved the use of materials that could flex with the Earth's shifting, rather than cracking or breaking under pressure. This approach was particularly important for urban areas, where dense populations and large amounts of infrastructure could make sinkhole damage catastrophic. In addition to reinforcing infrastructure, experts emphasized the need to better regulate construction and development in sinkhole-prone regions. Many of the sinkholes had occurred in areas that were heavily developed, with new buildings and roads being constructed without sufficient regard for the underlying geology. Researchers recommended a complete overhaul of zoning laws, ensuring that no new construction would take place in areas at high risk of sinkhole formation. The hope was that by restricting development in these areas, the number of people and structures exposed to the risk of collapse would be significantly reduced. For those living in already established zones, residents were encouraged to retrofit their homes to make them more resilient to sinkhole activity, such as reinforcing foundations or installing emergency evacuation systems. But even with these preventative measures, scientists and officials knew that they couldn't eliminate the risk entirely. Sinkholes, by their nature, were unpredictable and could still strike with little warning. So, the government turned its attention to creating a rapid response system to ensure that when sinkholes did occur, communities could respond quickly and effectively. The creation of specialized sinkhole response teams became a top priority. These teams, made up of engineers, geologists, emergency responders, and military personnel, would be tasked with containing and mitigating damage in the aftermath of a sinkhole. Their job would be to secure the area, stabilize the surrounding ground, and evacuate affected citizens as quickly as possible. In parallel with these emergency response efforts, the government focused on educating the public about the risks of sinkholes and what they could do to protect themselves. Public awareness campaigns were launched, informing citizens of the signs to look for and what steps they should take in the event of a sinkhole. These campaigns were seen as crucial to minimizing panic and confusion when sinkholes struck. People were encouraged to familiarize themselves with evacuation routes and to have emergency kits ready in case they needed to leave their homes on short notice. At the same time, a long-term solution was being discussed that could address the root causes of the sinkhole phenomenon, the potential shifts in the Earth's tectonic plates. Some researchers believe that the rise in sinkhole activity could be related to changes in the Earth's core, potentially caused by seismic activity, or even the impact of global climate change. While this theory was still speculative, it raised important questions about the future of the planet and its stability. In response to this, the government began investing heavily in scientific research to explore how tectonic shifts could be mitigated, and whether there were ways to reduce the risk of sudden subsurface collapses. Collaborating with international geological organizations, the government sought to fund long-term research into the Earth's shifting dynamics, hoping to develop new technologies or techniques that could predict and perhaps even prevent tectonic shifts from occurring in the first place. Meanwhile, some scientists proposed a more drastic solution: geoengineering. The idea was to attempt to stabilize the Earth's crust through large-scale intervention, using techniques that had never been tested on such a massive scale. These interventions could involve injecting materials into the ground to reinforce its structure, or even creating artificial fault lines to redirect tectonic activity away from vulnerable areas. While these ideas were highly speculative and controversial, the government found it necessary to consider all possibilities, given the unprecedented nature of the sinkhole crisis. Many environmentalists, however, were deeply opposed to geoengineering, arguing that the potential risks of tampering with the Earth's natural processes far outweighed any potential benefits. In the face of these mounting challenges, the government also recognized that the crisis required global cooperation. It became evident that no single nation could tackle the problem of sinkholes on its own. Climate change and tectonic shifts were global phenomena, and addressing the underlying causes of these disasters required a united effort. Collaborative research and information sharing between countries became a central theme in future discussions, with many world leaders calling for an international framework to address geological instability in a coordinated manner. While the solutions presented by the government were certainly ambitious, there was still a long road ahead. Preventative measures, such as geological surveys and infrastructure reinforcement, would take years to implement fully. The long-term research into the Earth's shifting tectonic plates would require decades of investment and collaboration before any real answers could be found. And as the world watched, there was a growing sense that the sinkhole crisis was far from over, that it was only the beginning of a much larger global challenge. In the end, the question was no longer just about whether or not the government could handle the crisis. It was about whether humanity, as a whole, could adapt to the rapidly changing geological forces that were reshaping the planet. As the government and experts grappled with the immediate damage caused by the sinkholes, a new solution began to gain traction: enhanced early warning systems. The basic premise behind this approach was simple: if the government could detect signs of imminent sinkhole formation before they happened, people would have a chance to evacuate in time, reducing the number of casualties and damage to property. While the idea of predicting sinkholes may have sounded far-fetched to some, emerging technologies were beginning to offer a glimpse of possibility. The foundation of these early warning systems rested on the concept of real-time monitoring. In regions identified as high risk for sinkholes, specialized sensors would be embedded in the ground to monitor changes in soil pressure, water levels, and seismic activity. These sensors were designed to detect minute shifts in the Earth's surface that might indicate that a sinkhole was forming beneath the ground. If any unusual activity was detected, such as a sudden increase in seismic tremors, a sharp drop in groundwater levels, or a slight downward shift in the Earth's surface, authorities would be alerted, triggering an immediate response. Ideally, this would give local governments the time needed to warn residents and evacuate them before the ground gave way. The system was not just theoretical. Pilot programs were already underway in several areas of the country, with promising results. These pilot projects focused on monitoring sinkhole-prone regions where experts believed that subtle signs of collapse could be detected in advance. The initial data collected was promising, with early warning signals being triggered several days before a sinkhole formed in a few cases. The system proved particularly useful in detecting changes in groundwater levels, which was often an early indicator of sinkhole formation. When groundwater is rapidly depleted or shifts underground, it can cause the ground above it to collapse, triggering a sinkhole. In addition to the sensors, advanced satellite technology was also playing a pivotal role in these early warning systems. Satellites equipped with high-resolution imaging capabilities could track large-scale shifts in the Earth's surface. By monitoring changes in terrain from above, scientists could pinpoint areas where the ground was slowly sinking or shifting in ways that might indicate a pending collapse. These satellite images could then be analyzed by algorithms that would identify patterns and anomalies, flagging them for further investigation. The advantage of satellite monitoring was that it could cover large areas quickly and efficiently, allowing authorities to assess vast stretches of land for potential risks. While the technology was still in its infancy, the government saw this as an essential tool for mitigating future sinkhole disasters. The hope was that with a fully functioning early warning system in place, regions at risk of sinkholes could be monitored on a 24/7 basis, providing constant updates on potential threats. Authorities could then issue alerts to residents, businesses, and local governments as soon as dangerous conditions were detected. This approach would reduce panic, giving people more time to prepare and evacuate, and possibly save lives by preventing people from being caught off guard. One of the challenges, however, was the cost. Implementing an early warning system on a nationwide scale was a significant financial undertaking. The sensors, satellites, and infrastructure required to support the system would be expensive to develop, maintain, and operate. Additionally, there were concerns about the potential for false alarms. If the system issued warnings too frequently, people might begin to ignore the alerts, assuming they were unreliable. This meant that the system had to be highly accurate in its predictions to maintain public trust and ensure that people took the warnings seriously when they were issued. Despite these challenges, the government pressed forward with the plan, recognizing that the cost of inaction far outweighed the investment required for the early warning system. If they could prevent just one catastrophic sinkhole from occurring, the benefits would far exceed the initial financial outlay. Furthermore, the technology could have applications beyond just sinkhole detection. With additional refinement, the sensors could be adapted to monitor other types of natural disasters, such as earthquakes or landslides, providing the government with a more comprehensive tool for disaster prevention and response. As the pilot programs expanded and the technology continued to improve, the government also began collaborating with private companies that specialized in advanced geospatial technologies. These companies had developed software that could analyze geological data and create predictive models for natural events, including sinkholes. By combining their expertise with the government's resources, a more accurate and reliable early warning system could be developed. This collaboration also allowed for the sharing of data, improving the system's overall accuracy and effectiveness. If the system worked as intended, it could potentially become a model for other countries facing similar geological risks, and the technology could be exported to areas in need of better disaster preparedness. In the face of growing sinkhole threats, these early warning systems were seen as one of the most promising solutions. However, experts caution that while they could provide invaluable time for evacuation and preparedness, they would not be a silver bullet. The technology still needed refinement, and it would take years of research and testing before it could be relied upon with full confidence. Still, the potential benefits were clear: lives saved, communities protected, and property spared from destruction. As the government continued to invest in the solution, the hope was that in the near future, no one would have to face a sinkhole without a warning. Another solution that gained attention in response to the increasing frequency of sinkholes was the concept of reinforced infrastructure. The idea here was to improve the design and construction of buildings, roads, and entire communities located in high-risk sinkhole zones. While sinkhole prediction technologies and early warning systems could help mitigate damage, they couldn't prevent sinkholes from occurring. Therefore, experts began to look at ways to reduce the risk to human life and property by making the built environment more resilient to sinkhole formation. The foundation of this solution was rooted in advanced engineering and urban planning principles. In high-risk areas, engineers began incorporating sinkhole-resistant materials into the construction of buildings, bridges, and roads. One approach was to develop specially designed foundations that could distribute the weight of structures more evenly across the ground. These foundations were designed to be more flexible, allowing buildings to better absorb and adapt to the shifts in the earth caused by subsidence. The idea was that even if the ground beneath a building did collapse or settle, the structure itself would remain intact, preventing catastrophic failures. For example, in sinkhole-prone areas, buildings were increasingly constructed with deep foundation piles that reached down to more stable layers of bedrock. These piles would anchor the structure to solid ground, providing a strong and stable base even in areas where the soil was prone to shifting. In addition to deep foundations, soil stabilization techniques were also being explored. These techniques involved injecting a mixture of chemicals or grouting into the ground to strengthen the soil, making it less likely to cave in when subjected to pressure or underground erosion. The hope was that by improving the stability of the soil beneath the buildings, sinkholes could be effectively prevented or at least mitigated. Another approach to reinforced infrastructure was the redesign of roadways and highways in sinkhole-prone regions. Many of the roads in these areas were built on unstable ground or had poorly understood subsurface conditions, which made them especially vulnerable to collapse. Engineers began developing new road designs that incorporated geotechnical monitoring systems directly into the infrastructure. These systems used sensors embedded in the roadbed to measure the ground's stability in real time. When signs of ground movement or shifting were detected, the sensors would send alerts to transportation authorities, who could then assess the situation and take corrective action. In some cases, roads could be reinforced with additional layers of material or redesigned to better withstand the forces that cause sinkholes. The concept of reinforced infrastructure also extended to urban planning. In sinkhole-prone areas, cities began to introduce zoning regulations that restricted the development of high-density buildings and infrastructure in the most vulnerable locations. Planners worked with geologists and structural engineers to map out the most risky areas, places where the underlying geology was particularly susceptible to sinkhole formation, and to create regulations that prohibited the construction of major buildings or infrastructure in those zones. The aim was to limit human exposure to sinkholes by keeping critical infrastructure away from areas that were too unstable to support them. In some cities, sinkhole-resistant landscaping techniques were also being integrated into public spaces. This involved planting vegetation that could help stabilize the soil, reducing the likelihood of subsidence. Tree roots, for example, could hold the soil together, while specific types of grass and shrubs were planted to reduce erosion, especially in areas near rivers or in flood-prone zones. These green spaces not only helped with soil stabilization, but they also provided environmental benefits, improving air quality and offering residents a natural buffer against the noise and pollution of urban areas. While the idea of reinforced infrastructure was promising, there were still many challenges to overcome. One of the most significant obstacles was the cost. Reinforcing infrastructure to withstand sinkhole formation was an expensive endeavor, and the required technology and materials were often not cheap. In addition, there were many communities that simply could not afford the necessary upgrades, especially in developing countries where sinkholes were an increasing problem. Without proper funding, the implementation of reinforced infrastructure would be limited, leaving vulnerable populations at greater risk. In some cases, the government's role in funding and supporting these initiatives became crucial. For example, certain national or regional governments began offering financial incentives and grants to businesses and homeowners in high-risk areas to help them make necessary structural improvements. These programs aimed to spread the cost of retrofitting infrastructure and to incentivize individuals to protect their property from sinkholes. While these initiatives did not guarantee full coverage, they helped to defray some of the expenses, making reinforced infrastructure more accessible to a wider range of people. In addition to the financial challenges, there were also technical limitations to reinforcing infrastructure. Not all sinkholes were predictable, and not all geological conditions could be easily mitigated through engineering interventions. For example, sinkholes that formed quickly due to sudden underground shifts or from natural disasters like floods or earthquakes were harder to defend against. In these cases, reinforced infrastructure could only provide limited protection. Additionally, some areas of the world had particularly complex or poorly understood geology, making it difficult to apply a universal solution to every sinkhole-prone region. Nonetheless, reinforced infrastructure became a key component of the multi-layered approach to sinkhole prevention. While it couldn't entirely eliminate the risk of sinkholes, it offered a practical solution for safeguarding people and property in high-risk areas. With the right combination of innovative engineering, urban planning, and investment, the built environment could become more resilient to the forces of nature that cause sinkholes. As we've delved deep into the theories, responses, and potential solutions surrounding the mysterious and often unpredictable nature of sinkholes, it's clear that the Earth's subterranean world holds far more complexity than we can imagine. From the natural processes that shape our planet to the ways human activities can trigger such catastrophic events, we are only beginning to scratch the surface of what's really going on beneath our feet. While we may never be able to fully predict or control when a sinkhole will occur, the steps we take today, through better technology, regulations, and preparedness, could greatly reduce their impact. The key takeaway here is that sinkholes are not just isolated incidents. They are reminders of the incredible power of nature and the delicate balance we must maintain with the environment. It's a call for action, for more awareness, and for proactive measures to safeguard our communities. As we continue to study and understand these phenomena, we'll undoubtedly uncover more solutions and strategies to prevent and minimize their destructive power. But it's also a humbling reminder of the forces that lie hidden beneath the surface, waiting to remind us how much we have yet to understand. If you found this deep dive into the science of sinkholes intriguing, make sure to hit that like button, because staying informed about the forces of nature that shape our world is a step towards understanding and preparedness. And don't forget to subscribe to the channel for more thought-provoking content about the mysteries of our planet. You never know what's lurking beneath the surface, and by subscribing, you'll stay up to date on all the latest discoveries and discussions. Thanks for joining us today, and keep your curiosity alive as we continue to explore the incredible forces that shape our world.